So let's look at the 1D distribution game as a preparation for looking at some of the examples in the original paper. We have a discrete 1D distribution with 5 choices, 1, 2, 3, 4, and 5. And for the real data, the training data, we have probabilities associated with each of these 5 choices, and the probabilities are 0, 0.2, 0.1, 0.2, and 0.5. It is easy to verify that these numbers sum up to 1. Also, just to make sure, the number 5 would be selected 50% of the time, and the number 1 would never be selected. The generator in this game has to output a single number. So the generator takes a random vector as input and then generates either 1, 2, 3, 4, or 5. The discriminator has to assign a probability to the number being from the true data distribution or being fake. So 1 is the highest probability, 0 is the lowest probability. So we'll think of one round here as the generator generating one output, and this game is played many, many times. To evaluate the game, we're using the GAN laws as introduced in the previous slide. Let's also say that the generator moves first, and in this example, the generator always outputs 1. That means the number 1. What should the discriminator do now? So this is not that complicated, because there are no 1s in the true distribution. Therefore, whenever the number 1 appears, the discriminator can safely assign a value of 0. That means it can be confident that that a 1 is fake. But it's a bit more difficult to think about what should the discriminator output for the numbers 2, 3, 4, and 5. So let me draw the discriminator probabilities for this example on top of the numbers here. So for the 1, the discriminator would always output 0. So what is it going to do for the 2? Well, if a 2 appears, the discriminator can with confidence say that this is real, so it would output a 1. For 3, it would output a 1. For 4, it would output a 1. And for 5, it would also output a 1. Now, this is still trivial in some sense, but what I wanted to highlight here is that it's somewhat surprising that the output of the discriminator does not really depend on these probabilities here. I mean, to the extent that even though there's a different probability of a 2 and a 5 being generated, the discriminator would still always output a 1 irregardless of these probabilities. In the next example, this is on the next slide, I'll just say it, the generator always outputs a 2. So what should the discriminator do now? So let's again mark it up here. So, okay, the generator always outputs a 2. We look at the numbers up here. For a 1, what should the discriminator do? Well, in some sense it doesn't matter because it would never occur, but 1 is clearly fake, so one would think that the discriminator should output a 0. So similar to before, if a 5 is output, the discriminator can with confidence say, so maybe there should be an arrow, it's not confusing. So if a 5 is out, if the discriminator sees a 5, then with confidence we can say that this is should be true, should get the true label, and Why is that again? Well, because the generator never outputs a 5, so whenever a 5 shows up, then we know it's real. Same argument for 4, should output a 1 and 3. Alright, so 2. And that's not so easy probably. Let's just think about the following. The discriminator always outputs 2. So let's start by trying to assign the probability 0 to the 2. So the problem with assigning a 0 to the 2 will be shown in the loss function as discussed before. There's this term log dx for data generated from the real distribution. So there are going to be some times there's a 2 that's also in the real distribution. So even though maybe it's not the dominant number being generated in the real distribution, it will happen once in a while. And then if this 2 comes along from the real distribution and the discriminator assigns a 0 to this 2, then the logarithm of that will be minus infinity, and the discriminator will get a very, very low score. Now, doing some derivations that are not shown, we can compute the optimal d of x for any p data x and p model of x. And the optimal discriminator choice is given by this equation, p data of x divided by p data of x plus p model of x. Using the previous example, p model was 1, p data was 1/5. So then the whole thing would evaluate to, again for this example, is 0.2 divided by 1.2. So it's going to be a bit less than 20%. Let's look at this figure that stems from Goodfellow's original work. Now, the figure takes some explanation. What we're looking at here is the random vector z that is fed into the generator, and the generator, and this is basically this 1D distribution game just in a continuous form and with a different true distribution. So what the generator does, it takes these random values, maybe they are from some range, maybe it's uniform distribution, and then it warps them to generate a new distribution on, and so this is the output is of the generator is x, and since the values are more concentrated in the middle, we'll now have a model distribution that is this green curve here. Okay, so in this visualization, we see that the most values will be output here. This is kind of visualized by these arrows. So the data distribution is given by the black points. So the data distribution is given by that here. And maybe let me get rid of that. And so now the question is what should the discriminator do? So we had the green curve is the model distribution, the dotted black thing is the data distribution, and the discriminator would evaluate the ratio of the probabilities. So that is the ratio between p data divided by p data plus p model. And looking at this curve here, so we see the discriminator as this dashed line here. It's a bit easier to check here in the middle part why this makes sense than it is to check out here, because the ratios are between two very small numbers, and then one has to look at the equation what these ratios really are. So for this part here, maybe here, we see that the p data is a lot bigger than p model. If p data is a lot bigger than p model, the discriminator will output something that is close to 1. Now, in some area here, again, this is the trickier part, let's pick something here. Here what we can see is that p model is a lot bigger than p data. And therefore, the discriminator outputs something that is fairly small. But then looking at these areas here, then both p model and p data seem to be very small, so we cannot really observe this ratio of p data divided by p data plus p model. And so we would look at the equation to know that this ratio would actually tell us that the discriminator should output something close to 0. And here we have the same thing, both of p data, p model are so small, but here the ratio is such that the discriminator would be outputting something very close to 1. Now, some comments about GANs. We're going to switch gears a bit here. What we see here is the recommendation to actually maybe split the loss function such that there's a different loss or value function for the discriminator and the generator. So the discriminator, this is similar to what we had before. There's this 1/2. But the generator now has a different objective. What it wants is it wants to directly optimize for this log d of g of z. This is motivated by some analysis that if the generator is not doing really well, let's say for example in the beginning, and the discriminator can dominate the generator, it's very difficult for the generator to get a meaningful gradient signal. And then this version is better in helping the generator to learn. Now, the whole thing is heuristically motivated. It's a modification that is not justified by an extensive derivation. It's mainly justified by this observation that the generator cannot learn or can only learn very, very slowly when the discriminator rejects all or almost all the samples. So now also, of course, the equilibrium is no longer describable with a single loss. And what we see here is the generator maximizes the log probability of the discriminator being mistaken. So there's some issue of non-convergence, and a lot of effort is being invested in getting GANs to converge. Optimization algorithms often approach a saddle point or a local minimum. One might hope it's a global minimum, but in these non-convex high-dimensional spaces, also, if they actually approach anything, is also in some sense disputed, and it depends on the exact optimization algorithm. But if you study optimization and you take like lots of simplified assumptions, then you often start with the idea that an optimization algorithm approaches a local minimum or a saddle point. But the tricky part here is that these game-solving algorithms that we'll have to use here, they may not approach an equilibrium at all, and it's much harder to determine what exactly they're going to approach, and it's much harder to find like simplified theoretical models that are in some sense a reasonable match for the practice. So again, a reminder that switching mean and max, such as described here, doesn't give the same solution. So if the discriminator, so in this first version, the discriminator has the control of the inner maximum, that means that the discriminator has basically an advantage, and it can try to figure out what to do when battling the best generator. So therefore the first version that converges to the correct distribution. However, if we switch it around, then actually the generator can use a strategy of placing all mass on the most likely point. So without doing any of the corresponding mathematics to explain that more precisely, we'll just take some extremely high-level view of this thing, and we would say that the optimization dynamics, how exactly the loss is set up and how exactly the GAN is trained, can lead to the generator creating an output that places a lot of the mass on the most likely point, or if there are multiple points in the domain that seem to be quite likely, then it might concentrate a lot of the mass in one particular region. So in this example here, we see a game where the generator has to output points in 2D space, and we see a target distribution that had multiple modes, and we call each of these kind of, you could imagine each of these is like its own mini Gaussian distribution. So each of these things we would call a mode, and then the target distribution has 8 modes, and what we can see now, if we are training one particular GAN, and again this is something that might or might not happen depending on how you set it up, we can see that first of all the distribution that the generator generates is kind of moving around, but we mainly see that the distribution is kept together, so the generator only generates one mode, and this mode kind of jumps around a bit, and then at one particular point the generator outputs this one mode that kind of might correspond to this area here, so it only generates points in this region. So here is some example of a mode collapsed training, and what we see here is a grid of 8 by 8 example outputs, and these are just some random vectors that are taken and fed into the generator. And so what we see is that all of the random outputs after 10K, after all of the 64 random vectors generate the same output image. And this is after 10K steps. And after 20K steps, the output image is different, but still all 64 random vectors produce the same output image. So after 50K and 100K steps, again, another output image. So there are two things we note here about mode collapse. So one is mode collapse is a serious problem in GAN training, and also that during training, this mode collapse can somehow shift. So you're generating, the same or almost only the same outputs, but which output this is can shift over time during the training. And mode collapse leads to a lack of variability in the results, and in the worst case, all results are the same. So here we would like to introduce on a high level the idea to use mini-batch features. So when the generator is generating samples, you would like it to generate one sample at a time, but to help training, it is possible to have the generator generate a mini batch of examples, and then the discriminator may be allowed to use statistics of the many images that the generator generates. So the discriminator now would receive a batch of real and a batch of fake images, and then it is allowed to do statistics across the batch. So let's think of a very simple statistic. One could, for example, simply take the average value of each image and then compute the variance of the average value of the image. So these features, you can decide then how powerful you make them, but just thinking about some features that look at some variance, this is probably the starting point if you want to implement something like this. So we want to refer to this paper, Improved Techniques for Training GANs, which was the first paper that introduced this idea. So we look at this example to illustrate the training progression. And what we have in A, we see that, again, the input random values along this Z line, they will be warped in some sense to give the output X of the generator. Green, again, is the model distribution, and dashed black is the data distribution. So this is the data distribution and this is the model distribution. So if we're kind of near convergence, so we see that the model distribution is already quite similar to the data distribution, then this dashed blue line would be a noisy discriminator that has pretty good values, but it's still kind of noisy, it's not trained perfectly. And so then when we would have a beta version of the discriminator, let's say we are allowed to train the perfect discriminator D given the model and data distribution in A, then we would get this no longer noisy discriminator by this dashed blue line. So going from A to B, we are training the discriminator, converging to this ratio P data divided by P data plus P generator or P model. So in the next step, from B to C, we are modifying the generator, but we're kind of modifying it slightly so that it's more like a gradient step maybe. So the green distribution, it moves a bit over to the left to be more similar to data distribution. It becomes a bit more peaked. And then when we go from C to D, we update the discriminator again to the perfect discriminator. So what we see is that really in the, so what I mean is from C to D, there are many, many steps in between, and we'll get basically the equilibrium, the best possible generator, and the best possible discriminator, looking at the best possible generator. And so what we see is that the discriminator really can no longer decide, and this ratio P data divided by P data plus P model is always 0.5. So this is the discriminator output 0.5 at equilibrium. So unfortunately, we are not able to always find the optimal discriminator for a generator. So we will have this stochastic gradient descent algorithm that is training the generative adversarial network by doing alternative update steps for the discriminator and the generator. But what we can also do is, if the generator and discriminator are both updated with one step, then we might as well update them together. So in this algorithm, we just have a number of iterations. We sample a mini batch of m noise samples. So these are m noise vectors from the noise prior. And then we sample a mini batch of real examples from the data. So these are the noise vectors set, and these are the real images x1 to xn. Then we update the discriminator according to the equation, and then we update the generator according to the equation before. And to perform the update, we have to compute the gradient with respect to the discriminator variables, and we have to compute the gradient with respect to the generator variables. This is a slightly modified, simplified version of the original GAN paper, because in the original GAN paper already there was the idea that maybe you want to have a different number of steps for updates. So you could say, for example, I want to have 10 discriminator update steps for one generator update step. But if you start with a basic GAN implementation, actually it's more common to have the same number of update steps. All right, let's look at the results from the original GAN paper. So what we see here are images generated from a GAN trained on MNIST, and these images look really good. And in the beginning, and still nowadays, there's always the problem that generative models can generate fantastic output, but the concern is always that they generate outputs that simply copy input data. So for the images in the last column, what we show in the yellow boxes are the closest images in the training data to these images. And so we just want to verify that, you know, they could be similar, but they're still different, and it's not mere copying. The differences are bigger for the faces, comparing this column and this column. And face models, you know, it already looked quite promising. And then I think this might be CIFAR, not sure. Here, it's of course a lot harder to see what's going on. And so the initial results look kind of interesting, but the initial results were very far from what people were able to achieve just simply 2-3 years later. The original GAN paper used the standard multi-layer perceptron architecture, linear layers, but for generating images, convolutions are an obvious choice. And the convolutions work extremely well for image data. So DCGAN is the first major improvement to the architecture design of GANs. This paper had a lot of contribution. It's really a very significant paper because of the many things that were introduced in this work. So here are some of the improvements over the original GAN architecture. The authors propose to use batch normalization in both the generator and the discriminator networks. While batch normalization is no longer the state of the art, it at least gave the hint that normalization in general is very important for generator and discriminator networks. DCGAN also doesn't use fully connected hidden layers, and it also doesn't use pooling. Instead, it uses the strided convolutions. Activations it uses ReLU and leaky ReLU. So here is a drawing of the generator to the left and the discriminator to the right. As input we have a 100-dimensional random vector, and then this black dot here shows the transpose convolution. And I mean, the first one is a bit special because the input is a vector. But then after the convolution, there is a batch norm, then there is a ReLU, and then as output we get this 4 times 4 times 1024 dimensional tensor. Again, the next thing is there's a convolution, there's a batch norm, there's a ReLU, and then we get this 8 by 8 by 512 tensor, and so you do this all the way until you have an image of 64 times 64 times 3, an RGB color image. The discriminator mirrors the architecture of the generator, and we can see again how batch norm is being used and how leaky ReLU is used as activation function in the discriminator. Then the output of the discriminator is has this specific activation function, which is a sigmoid, and the last layer, so this is just the last layer basically of the discriminator, has the sigmoid as exception to the leaky ReLU, and the last layer of the generator has the 10H as an exception to the ReLU. So one interesting thing, so let me first strike that out, I don't know why that's still here. So one thing that's interesting, and that is also a component of DCGAN, is the idea of latent space arithmetic. So what you can do is you can sample a lot of images and observe them, and then let's say you find some images that correspond to a man with glasses. So you pick a man with glasses, so this would have some latent code set 1. And then, sample a bunch of other images, so you get some man without glasses, so you get this is a latent code set 2. And then, sample a bunch of other images, and then until you obtain this women without glasses, and this would be the latent code set 3. And so what you can really do is you take, this is a 100-dimensional vector, you do set 1 minus set 2, 100-dimensional vector, plus set 3. And then you have this idea that man with glasses minus man without glasses plus women without glasses is a woman with glasses. This was inspired by the arithmetic that you can do with word embeddings.